All right, good morning, everybody. Thanks for coming out. I know it's a little bit early in the morning. I hope we've got all our caffeine and we're ready to go. Real quick introduction. My name is Edward Thomson. I'm a program manager at Microsoft. I work on Visual Studio Team Services. Before I was a program manager, I was actually a developer. I wrote a bunch of the code that is in Visual Studio Team Services to handle Git repository management. Before that, I was at GitHub and SourceGear, also working on version control. So I've been writing version control systems for a really long time. It turns out I'm a huge version control nerd, to the point where I actually just started a podcast about version control. Totally think you should check it out if you're also a version control nerd. It's called All Things Git. I'm going to go out on a limb and say that if you're spending your morning in this session, you're probably the target audience for this. So, can I see a quick show of hands? How many people are using Git right now? Right, it's really everybody. And that's great because if you're not using Git already, I think this will not be the most interesting session in the world because we're actually gonna go a little bit deeper. We're gonna kind of peel back some of the layers and look at why Git is the way that it is. So why do we want to do that? Well, if you've used Git for a little while, I think you might have some ideas of some of the challenges that you've been facing. But if we rewind to the introduction of Git itself, you may be familiar with this. Git was built by a guy named Linus Torvalds. And if this name sounds familiar, it's because he wrote the Linux kernel. And he built Git to help manage the development of the Linux kernel. He wanted to replace some of the existing systems that he was using. He used to use CVS. After that, he used a proprietary distributed version control system, but he wasn't happy with either of them. So when he decided he wanted to build Git, he had a list of goals. Git had to be fast, had to support a distributed workflow because the Linux kernel developers are spread out across the world, and it had to have safeguards against accidental data corruption. What's missing from this list is that Git had to be easy to use. Totally not on this list. In fact, there's one thing that he had on this list that I haven't listed. He said that if ever there was a discussion of what you had to do with Git, how Git should be developed, you should look at the CVS project. CVS was an existing version control system, the concurrent version control system, as an example of what not to do. And I know the CVS developers, they wanted to make a system that was actually easy to use. So Linus almost was trying to build a difficult to use system. And everybody maybe doesn't agree, but Git is well known as being difficult to use. There's XKCD panels about how challenging Git is. And it's totally accurate, because Git has some really strange commands. The syntax is odd, it's hard to understand what's going on, and there's even overloading. Git checkout, the first example, git checkout branch, switches branches. Git checkout -b creates a new branch. And then the last two actually check files out without switching the branch. So it's really challenging to really unpack what Git's doing. And if you get it wrong, Git gives you some strange error messages that don't exactly tell you what you need to do to fix the problem that you're having. The last one's my favorite. You're in a detached head state. What on earth does that even mean? And if you want to try to figure out how these commands work and what these error messages are giving you, you go to the documentation and it's not very helpful either, because it tells you things like forward port local commits to the updated upstream head. I actually know what that means only because I had to do this research to make this slide. That's the documentation for Rebase. But if I didn't know that and you told me that a command was going to do that, I wouldn't have any idea what it did. Now, there's actually a bit of a lie on this slide. One of these isn't actually part of the Git documentation. It turns out the Git documentation is so complex, would be the polite way to say it, that somebody has taken it all, fed it into a Markov chain generator, and created the Git man page generator, which outputs fake Git man pages. It turns out that I think it's the third one, reveal all downstream commits below the sent upstream paths. I think that's the fake one. I think that doesn't make any sense, but it should give you an idea of the quality of Git's documentation that even I don't know that to be true. It was a little while since I made the slides. So check out the Git man page generator. It's a lot of fun. So why do we use this crazy system called Git? Well, it's really powerful, even though it's a bit challenging. And it turns out the easiest way to really understand Git is to realize that it's just a leaky abstraction, the commands are, over the data storage model, which is actually beautiful. And so you can get a lot of power out of Git by understanding how that works. So I don't want to do an introduction too much, but I do want to set the stage for why Git is the way it is and look at what it means to be a distributed version control system. Again, it was built by Linus Torvalds, who has developers all over the world working on the Linux kernel, and that's common in open source projects. It tends to be that people are distributed very geographically, and so a distributed version control system supports the nature of a distributed team. So, what do I mean when I say distributed? Well, in a centralized version control system like CVS or Subversion, like Team Foundation version control, you have a server that handles everything. If you want to check a file in, you send it up to the server and it handles all that for you. If you want to do a merge, the server takes care of that. And some of them even are so centralized oriented, so server oriented, that you may have to tell the server when you just want to check out a file and start editing it. That doesn't work when you have a team spread out across the world. And that's where distributed version control comes in. The idea is that everybody has an independent copy of the repository. When you run git clone, you get the identical bits that are on the server. That's why the command is called clone. And so that gives you a lot of power. So you can commit locally, you can merge locally, you can branch locally without having to worry about what's on the server. Of course, you still have a centralized server that has sort of the master copy, the source of truth. Maybe that's in Visual Studio Team Services, maybe it's in your on-premises server, maybe you're using TFS, maybe it's in GitHub. You know, whatever that is, it's still a good best practice to have a central server that has the bits that you're going to release so that you know what's there. You know, in the bad old days, we used to sneakernet files around on floppy disk, and nobody was ever sure what the latest copy was. So we don't want to go back to that. And a lot of people think of distributed version control as being a bit chaotic. And of course, it shouldn't be. You should still have a central server, but you don't need one. And that's the architectural change that allows for some of this real cool power. So again, to sort of differentiate distributed version control from centralized. In a centralized version control system, every change set, every commit, whatever you want to call it, builds on the previous one, and the server, again, takes care of all of that for you. In a distributed version control system, you have independent commits. So I have a copy of the repository that I get when I run git clone, and so does my coworker Alice. So we both have independent copies of the repository. We can commit independently. And that's really the biggest architectural change in Git. If we take a look at what that looks like, what that means is if I get started cloning my project and Alice clones the same project at the same time, we get the same 3 commits. If I make a change and commit it, I'll get a new commit number 4. Alice, when she makes a change, she can commit it independently to her local repository, and she'll get commit number 5. At some point, we need to join up our histories, so I'll get a copy of her commit number 5, again, probably by going to our central server, but it doesn't have to be. I really could, you know, put that on a floppy disk and bring it over to my computer. And ultimately, I'll need to merge these 2 commits up. I'll take mine, number 4, hers, number 5, and produce a new blend from number 6. Okay? And that's actually how history is basically modeled in Git. There we go. So if I run git log, and I think this is something you see all the time, I just see a list of commits over and over again, and this is what you see on the website. If you say go to GitHub or Visual Studio Team Services, you tend to just see commit after commit after commit after commit. But in reality, Git stores its data in a graph. And when I give the -- graph flag to Git log, I can actually see that. So this is exactly what we just saw. Commit 1, commit 2, commit 3, coming from the bottom. And then it actually splits off into my change and Alice's change. Those are both independent changes that were both based on commit number 3. And then they come back together where I've merged them. You can also use something like Git K, which comes with the Git for Windows package, to see the same thing. And if I zoom in, that's right, it's going to zoom my second monitor. That's super unhelpful. Let's try that again. There we go. Up at the top left, you can actually see how it's showing that history diverges in the same way. And you can see this with a bunch of cool Git clients, Gmaster, Git Kraken, whatever you prefer. Most of the Git clients are able to show you exactly what's going on at the graphical level. So, what's actually going on there is that Git really is storing its history in this graph. It's called a directed acyclic graph, or simply a graph. I don't want to dig too deeply into this. I don't think that the graph theory here is really all that necessary to understand. I think sometimes it gets in the way, but I do want to mention that, first of all, yeah, what does it mean to be a DAG? It's directed. So this is actually, let's turn those arrows around. What's actually happening, we tend to think of time as flowing forwards, and we draw the arrows that way. In Git, actually, the arrows flow backwards. So every commit points to the previous commit. We'll take a look at that in just a second. But I do want to just show that there is direction here. What does it mean to be acyclic? That's the A in DAG. So what you can't do is have commit 1 pointing to commit 3. So again, these arrows are pointing in such a way that they're building a history. When you check in commit number 4, it points to its parent, which is 3, points to its parent 2, points to its parent 1. So what can't happen is you can't have a pointer going into the future, right? That makes sense. When you create commit number 1, it can't be pointing off into something that doesn't exist yet. So that's all it means to have a directed acyclic graph. This is a really clever storage mechanism for building a distributed workflow. So one other thing I kind of glossed over is, how are these commit IDs actually generated? I said that when I checked in a new change, I would get commit number 4. And when Alice, in her separate repository on her computer, checked in her change, she would get commit number 5. The problem is that that's not exactly how it works, because we can't have these sort of integer IDs, these monotonically increasing numbers. That works on a centralized version control system. It doesn't work for a distributed system, because I have no idea what Alice is doing. She's got a completely separate repository. So it turns out that's not what we actually use. We could use random numbers, we could use GUIDs. What Git does, which is really clever, is that it actually takes a hash of the contents of the commit. It's a SHA-1 hash. And it's a cryptographically strong hash, and it gives you these, well, it gives you these 40-character long hexadecimal kind of strings, which are a bit of a pain to work with. Thankfully, we only need to use the first, say, 7 characters. And that's what it uses for its commit IDs. It's a very clever way of doing things, and it allows for some real neat advantages. We'll take a look at that in just a second. So I said it takes the contents of the commit, and it hashes that to get the commit ID. What do I mean? What does a commit look like? Well, first of all, a commit represents the entire repository. It's a snapshot of the entire repository when you run git commit. This is sort of subtle, because Git doesn't really show you this. If you run git diff, if you run git log, if you run git show on a commit ID, it shows you what's changed. So it's super simple to think that that's actually what Git's storing. You know, if I run git show commit, shouldn't it show me the commit? What it's actually doing is it's running the diff at that very moment in time when you run that command. That's not actually what's stored. Git is really storing a pointer to the entire repository, a snapshot of the entire repository in that time. And it uses some other quote-unquote Git objects to build this snapshot. It uses trees, which represent directories, and it uses blobs, which represent files. And it'll just chain those together to build an entire file system hierarchy. So if I have one file and I put it in my Git repository, let's call it file1.txt. When I add that and run git commit, what I'm going to get from in a new repository is I'm going to get a blob that points to that file, file1.txt, that has that contents. I'm going to get a tree that has a list of the files in the repository at that time. There's only one, file.txt. And then I'll have a commit that points to that root tree and has some other metadata. If I want to come along and add a second file, I'm going to get a whole new snapshot of that repository. But, and this is why using a SHA-1 hash is so clever for Git, I don't actually have to duplicate everything. So if I add a new file and I don't change file 1, what happens is I'll have a new blob pointing to my new file, file 2, and I'll have a blob pointing to file 1, but since I didn't change its contents, that means its hash also doesn't change. If you run SHA-1 hash on an unchanged file, you'll get the same hash back. So I will not need to store a whole new copy of that file 1. So I'm getting some sort of space savings in my Git repository just by using SHA-1. I do get a new tree because now it's pointing to both file 1 and file 2, and I do get a new commit since A, the metadata is changing, and B, I'm pointing to a whole new tree. So it's really nice to be able to get these space savings, even though I'm only changing, just a few things. I don't need to restore everything. So I get all the benefits of storing full snapshots without any of the space consequences that might entail. Okay. Let's take a look at what that actually looks like. So if I'm in my working folder, if I just clone a Git repository, one of the neat things that's in here is, first of all, I've got all the files that I've been working on, but I've also got this folder called .git. It's a hidden folder, so on Unix you'll have to run ls-a to see all files. On Windows it's hidden by default, so I've actually gone and unhidden this so that I can poke around. So this is actually where all the data in my Git repository lives. When I say, you get a full copy of history, when you get a full copy of the repository, it's right there in my Git folder. And it's really cool to look around in. I do recommend, though, that you look and don't touch, because it's really easy to break something if you start editing files, willy-nilly. So in here, if I run dir, this is actually the information in my repository. Let's look in the objects directory. So that's where the commits, the trees, and the blobs live. And if I look in there, I've just got a bunch of 2-character hex strings. What Git's doing is it's splitting up all of the objects into these directories. So F2, the F2 directory contains all the Git objects that start with F2. I want to go into 37. I actually happen to know that my most recent commit is 3741305. Okay, let's take a look at what that commit actually looks like. Right. Well, it's actually a bunch of nonsense. It turns out that what Git's done is it's actually compressed the data, but it gives me a really helpful, it's called a plumbing command. Git separates its commands into the porcelain, which are the ones that you typically run, like git add, git commit, git status, and the plumbing commands, which are there for you to use if you want to do some nice advanced stuff, but they're also the commands that Git itself runs in order to to do its work. And one of those is called git cat file. So I can git cat file commit and then give it a commit ID, 3741305, and thankfully I don't have to give all 40 characters. I can just give the first. And so this is actually what a commit looks like. Again, I've got a tree, and then that's an ID to a tree object. Parent, that's how it builds the graph. A git commit points to its parent. Again, that arrow going backwards in time, pointing to its parent. And then some more metadata. Who committed it? It was me. And a commit message down here at the bottom. So I can unpack this a little bit further to look at the actual hierarchy, to see the snapshot of the repository at this point in time when we did the git commit. And so I can keep using the git cat file command. I can git cat file tree and then get that tree ID out of the commit. It's F2A25C. And to be honest with you, when I do this, I'm going to be pretty disappointed. It turns out that you can see over here, this is starting to look like gibberish. Turns out that trees, unlike commits, are not just plain text files. They're a little bit more encoded. They're binary encoded for a little bit of speed. Let me move this up to the top so that people in the back can see. So I can use a different command instead. I can use git ls tree, F2A25. And then I actually get to see that this tree is actually just pointers to blobs, and it gives their blob IDs, file1.txt and file2.txt. Way over on the far left, I see something that looks a little bit like a Unix mode, which definitely is inspired by, but it turns out that it can only be a few different values. It doesn't store a full set of Unix permissions in here. But that's where it would say if it was executable, if I were checking in scripts or binaries. So I can go one step further and actually look at one of these blobs. I can get cat file blob 5C117. And since I'm just checking in text files, I can use cat file just fine. Otherwise, I would see a bunch of binary gibberish if I were checking in binaries. I hope you're not checking binaries into Git, at least not without using Git LFS. It's not ideal because there's so much history. You're getting all that history. Adding binaries to your Git repository means that your repository gets very big very quickly. Okay. So that's actually how a Git repository is laid out. That's how the structure is actually saved as commits, and how the DAG, the history, the directed acyclic graph, is actually generated. It's a very straightforward set of objects that you're actually manipulating. So that's actually how we create a commit, but creating a commit is really only sort of the bare minimum to be a version control system. The more powerful part of that is actually creating branches. And that's what allows two different engineers to work on two different things at the same time, or even me. I can switch branches, I can start working on a feature, set it aside, work on some bug fix, and then come back to it. That means I don't have to check that feature in with my bug fix, because that feature may not be ready. All of a sudden I'm rolling something out to production just because I had a bug fix. Branches allow two different streams of work to go on in parallel. So unlike a centralized version control system like TFVC, like Subversion, I don't have folders with branches in them. You might be used to seeing like a folder called trunk, and then next to that, folders that are different branches. Instead, in Git, branches exist at the repository level. And this actually allows us some benefits. First of all, they're exceptionally lightweight. So like the way Git gets clever with storing hashes, using hashes to store the actual structure of the repository, Git gets clever by using these repository level branches, keeping them very lightweight. You know, in TFVC, you would need to be an admin to create a branch, and it would take maybe a little bit of time. It wasn't super heavyweight, but Git's branches are incredibly lightweight. And so we encourage you to create a new branch anytime you want to do a bug fix, anytime you want to create a feature, because they're so lightweight. You might as well take advantage of them. So what really happens is they're just a pointer to a commit inside this graph. So if I have the mine branch, when I was working with Alice from before, I had created my new commit, I had gotten her commit, and then I had actually merged them together. So we were actually working on branches before, even though we didn't talk about it that way. And then the mine branch points to that new commit that I made. Alice's branch, however, stays behind at the branch, at the commit she created. So let's actually take a look at what Git is storing inside the Git directory when we do that. So if we go back to the .git folder, so right below my objects directory is the next directory down is called refs. So within Git, this is just Git terminology. Refs are tags and refs are heads or branches. So if we go into the refs directory, we'll see exactly that. We'll see heads and we'll see tags. Tags are very similar, but more or less immutable. Heads are branches, and they actually move around a little bit more. So if we look inside my heads directory, we can see Alice and we can see mine. Okay, so Git's branches are actually just stored as text files deep down in the .git directory. And if I type mine, you'll see that it's just an object ID. It's just the 40 characters pointing to a commit in the graph. Same with Alice. And if I run git log -- graph -- one line and add the I'm getting tired of typing this. So I've actually set up an alias for exactly this because I run it so often and I'm tired of typing it. Instead of log -- one line, I use LOL. So git LOL should show me that my branch points to 9969 and Alice's branch points to 1C6. And that's exactly what we see. Up at the top, mine is 9969, Alice's is 1C6B. So this is actually, that's just how branches are stored, is 40 characters. That's what I mean when I say they're lightweight. If I create a new branch, it writes 40 characters to disk. Actually, it's 41, there's a new line. But that's how efficient Git is at storing branches. So that's why we encourage you to create new branches whenever you're spinning up a new bug or a feature, because it's immediate. And so when you're working with branches, one of the other important things you need to do is you need to have the concept of being on a branch, right? We have this idea that I switch branches and I work on a branch. I'm checking in changes to a branch. How does that actually work? Well, that's actually just another pointer. You've probably heard this, and in fact, we talked about the detached head state earlier. There's a special meta branch called head in all caps. And instead of pointing to a commit, head points to another branch. And that's what stores the actual branch that you're on. So if we go back in here into our .git directory, we can actually see about halfway down, head in all caps. And if we take a look at what's inside, it says refs, heads, mine. Remember, that's just the path in the .git directory to the mine branch. So that means if I run git lol, head points to mine. If I switch branches, oh, sorry. Let me run this from my actual work tree and not the .git folder. So if I switch branches to the Alice branch, okay, if I run git lol, now head says it's pointing to Alice. If I run git branch, it will say, again, that I'm on the Alice branch. And if I type the .git head file, it's changed from mine to Alice. So when I switch branches, what I actually do is, first I just check out the changes between the my branch and the Alice branch, and then I update that .head file, or that .git/head file. So very straightforward to switch branches. Now, being able to work on parallel lines of development is wonderful, but you need to at some point be able to merge them back together. And we've talked about merging two commits already a little bit. We've certainly touched on it, but we haven't really talked about how this actually works. Earlier I was on my branch, I had my commit, and I was merging in Alice's branch. So what we actually do there is we create a new commit that has all the changes from my branch, all the changes from Alice's branch, and check it in as a new commit. This is a standard three-way merge, very similar to what you've seen in other version control systems that you might have worked with. TFVC does this, Subversion does this, CVS does this, everything does this. However, the nice thing about Git is that it encodes some of the information about how to do a merge in its history. So when we talk about a quote-unquote three-way merge, what we do is we take the branch that you're on, and we take the branch that you're merging in this case Alice's, and we need to find the common ancestor. And that's what allows us to actually do the merge. That means that it will isolate the changes that have been made in the Alice branch from the common ancestor, and the changes in my branch from the common ancestor, and blend them together. If you don't have the common ancestor, it's impossible to know what has changed on each branch. And in Git, the common ancestor is as simple as just walking down the graph backwards. So I start at Alice's branch, and I walk backwards, and I find the first commit that is in both Alice's and mine. Boom, common ancestor. It's really obvious in this example, but of course this is about the simplest example you can come up with. But for the most part, you can just draw the graph and walk backwards to find it. It's very straightforward to find the common ancestor in Git. In TFVC, not so much. In Subversion, not so much. You've got to record this information. The version control systems actually record every branch that you create and every merge that you perform, and then try to find exactly what's happened. And if you've ever gotten into a situation with TFVC where you have to do a baseless merge, it hasn't found you a common ancestor. And that's painful. So Git avoids that problem entirely. It encodes this common ancestor information right into the graph. Okay, let's take a look. I'm sure most of you have done a Git merge, but let's actually unpack a little bit deeper what it's doing. So if I switch back to my branch and I switch back to that commit. So I haven't yet merged Alice's change into mine. So it's made this change. All I've done is bring in the alice.txt file. And now when I run git lol, now I've got that whole branching structure. So again, it's found the common ancestor, which was 9C87 AC5. And it's brought in Alice's change and made a new commit on top of that. Okay, so that's merging. There's a special case of merging, though, where we don't create that second commit. It's called a fast forward. I think you've probably seen this. When you run git pull, often you'll see updated with a fast forward. What does that actually mean, though? So in version control terminology, it means that you are your own common ancestor. What? It's almost like Back to the Future kind of action going on. So what happens is, if you are, let's say we're on the master branch and we're pointing to this E4509. And what we want to do is we want to merge the feature branch into our master branch. So, I mean, you can look right on the graph and see that there's nothing to do because the feature branch derives directly from this commit right here, and we haven't made any subsequent changes off of it. So if we walk back down history looking for our common ancestor, we start at feature, we walk backwards, and we find the first commit that's in both branches, and it's us. It is the master branch. So all we have to do in a fast forward case is to just move that pointer forward. So we don't actually change anything at all except writing 40 characters to disk. So that's the most possible efficient way to do a Git merge. And this happens a lot when you have, let's say, when you aren't changing your master branch directly, when you create branches off of your master branch, so that it always tracks the upstream, your server's master branch. When you run git pull in your master branch, that's what you'll see. So if I switch to this commit right here, I think I don't have a good demo for a fast forward merge. Let me try that again. So if, let's say, I'm on a branch, and if I run git log on the my branch, you'll see that 9C87AC5 is in my history, is in the my branch's history. And I'm on this new branch that is 3C41305, sorry, which is also a little bit further down in the my branch's history. And I want to merge my branch into this new branch that I've created. It'll update with a fast forward. All it's done is update that pointer file in the heads directory to point to that new object ID and done the checkout. So super efficient. Can't really talk about merging in Git without talking about something a little more contentious, which is rebasing. I'm not going to get into whether you should merge or rebase. That's a decision you have to make with your team. But I do want to tell you how rebasing works, because so many people are terrified of it. And understandably, because Rebase Interactive has a lot of options. But a simple rebase is actually really straightforward. The idea being, and this is how it gets its name, you're taking some changes that are on some branch and plucking them off and putting them on a new base branch. So in this case, what I want to do is I want to rebase my changes onto Alice's. So instead of doing a merge so that we end up with that graphical change in history where commits diverge and then come back together, I want a linear history. I want to take the mine branch, I want to take my changes and put them right on top of Alice's so that I've got this nice linear history. And that's all Git really does, is it, again, finds the common ancestor, so it walks the trees backwards, finds the common ancestor, and isolates the changes that are in my branch. And it replays them, it cherry picks them, or applies them right on top of Alice's branch. And so there's some actually really cool things that you can see when this is happening. So if I switch back to my branch and I switch back to a commit that I haven't merged with Alice's yet. Okay, so right now Alice's changes aren't in my branch, and instead of merging, I want to rebase. So the first thing you see is it rewinds the head to replay the work on top of it. So what it's doing is actually checking out the common ancestor there and then forwarding to Alice's branch and then applying. So it's actually taking the change that I made and applying just that one change on top of Alice's branch. Let's actually do something a little bit more contentious here. Let's actually get a conflict when we do this. I happen to know that Alice introduced a change called alice.txt. So if I add the same file, then I'm going to get a conflict. So let me. Well, that's actually a lot of error messages, but. So what's happened now is that Git was able to replay that first change just like before, and that second change I just added conflicted the file. And that lets me go into my .git directory and actually see what's going on when I do a rebase. So there's a new folder here that wasn't there before, rebase-apply. I'm pointing this out because, honestly, when I get into a problem with Rebase, I like to know what's going on. So in this Rebase apply directory is actually, these are the actual patches that Git has isolated and is replaying on top of Alice's branch, 0001, 0002. Those are the two commits that I made that it's trying to bring onto Alice's branch. And I can even look at them a little bit more in depth. So when I have a conflict, I can understand what's going on. So what it's actually done, again, is it's isolated the change that I brought in. I added this mine file, and these are Git diffs, so they're not the easiest thing to read by themselves, but they do give you insight into what's actually happened. So that's the file mine.txt, and if I look at 0002, now I understand why there was a conflict. It's adding this file called alice.txt, the same way that what I'm seeing in Alice's branch. If I run git status, I get a much nicer view of this. It's hard to read because it's in red on black, but it does say both were added alice.txt. And that's, again, why I've got that conflict. Okay. So again, rebasing a conflict, very straightforward. One of the things, though, that happens when you rebase is you get a whole new commit because Git is built on these hashes, and Git commits include a pointer to their parent. When you change the pointer to the parent, like we did, we created a whole new commit with a whole new parent. I get a different commit ID. So I've actually rewritten history, and that's what rebasing does. It's called rewriting history. What happens to the previous commit? Well, it's still there. It's just that there's nothing pointing to it anymore. And so it's really straightforward to be able to recover quote-unquote lost data with Git. So this is really important and really powerful. So let's actually run a command called Git Ref Log. And this will show you what, it's a little bit hard to read at first, but it's actually showing you a sequence of all the commits that you have made and been on. So you can actually see when the rebase started. It's a few lines down. And what's happened is it will show you the commit IDs as they go. So we can see when the rebase began, where we were. And we can go back to that, even though it's not in history. If I run git lol, some of the thing, let's scroll up just a little bit more. What I don't see in my git log is that 47bf0c3 commit. So it's still in my repository. It hasn't gone anywhere, and I can run git cat file commit to see it. 47bf, right? But when I run git log, it's nowhere to be seen. So that change isn't gone. It's still in my repository where it will stay in case I screwed something up in my rebase, which I do all the time. I always get something wrong when I'm resolving merge conflicts. And so I can make all these changes without actually losing any data. And I can use git ref log to find it. There's one more thing I can do if I'm worried about losing data. There's a command called git recover. And this actually isn't part of Git. You have to go download this yourself. But I can run git recover, and it will show me all of the files that are no longer in my Git repository. Things that I once added, running git add, and maybe even committed, but don't exist on a branch anymore because perhaps I rebased them away and rewrote history. And it will actually show me all of the changes and allow me to recover them. So this is a really cool feature, and you can just git recover -a, and it'll find everything and just write it to your local directory. So it's a very powerful way to find things that you may have accidentally misplaced. Git doesn't really ever get rid of anything, so you can always use the ref log to find commits that you've lost and git recover to find blobs that you've lost. So We're about out of time. I realize this was like a super quick introduction into Git's internals. What I'd like you to do though is just remember that these Git commands are just a leaky abstraction over the data storage. So if you ever get confused about what's going on in your working tree, it's easy to look in the .git folder sometimes to find out what's in there. So if you have questions, I'm happy to answer them. I'll be around here, or you can hit me up on Twitter. I'm at eThompson. I'm happy to talk about the way Git stores its data. So thank you so much.